for Weston?
Yeah, very good. Very good. Well, thanks everybody for joining. Real excited. Weston is number 26,
It is.
sixth Sodick and Friends webinar here. So thanks to Dan for presenting today from Frigel. My name's Bennett Howard. For those of you that don't know me, I work for Sodick on the injection molding machinery side. Regional sales covering Minnesota, Wisconsin, Michigan, and the Southwest. On the top of your screen as well, we've got our national sales manager, Len Hampton. Len is sort of the sponsor of this whole Sodick and Friends webinar series. So thanks to Len for joining us today. And then finally, from the Sodick side, we've got Weston Harbaugh. He's our host today. He's also a sales engineer like myself. Covers the East Coast, Illinois, and another portion of the Midwest. So with that, I will introduce our speaker here today from Frigel. We've got Dan Hastings joining us. Real excited to have Dan on here to kind of teach us some about cooling systems, and I guess I'll leave it at that because he's the expert. So Dan's been with Frigel since 2008. Inside sales, outside sales, and I have down here, I thought this was pretty cool, received his Certified Energy Manager certification in 2013. So not exactly sure what that entails, but it sounds like a big deal, and it sounds like we got the right guy on. So anyhow, looking forward to this presentation today from Dan. So I think with that, Weston, I'll hand it to you real quick. You can talk through questions and answers and stuff like that, and we'll get started. Thanks again, everybody, for joining.
Yeah, excellent, Bennett. Thank you very much. And welcome, Dan. Welcome to the audience that is joining us here today for Sodick and Friends number 26. Looks to be another great topic here. First, want to say thank you for everyone who's joined us over the past 18 months. It's really made this webinar series a great success. We've had a really great lineup, so looking forward to more great presenters coming up, including Kibo, which is a great tool builder, a great partner of Sodick's, and to Topaz. Their stake is the world's leading maker of COC materials, and another great partner of Sodick on a couple of microfluidic projects in the past here. Today, looking forward to this great presentation by Dan from Frigel, and want to ask that can submit any questions you might have for Dan through the Q&A portal. It's located in the lower right-hand corner of the WebEx screen, and if you would direct those to the host, those will come into myself. And after Dan is finished with his entire presentation, we will address all those questions in the order in which they were submitted. So as he finishes up, we'll turn it over to that. All right. With that, Dan, I guess the show is yours. Thank you very much.
Well, thank you, Weston. Thank you, Bennett. And thanks for having me on. Great honor to be here presenting some information to you on this nice Sodick webinar. So my name is Dan Hastings. Again, I'm the regional sales manager for Frigel North America, covering Minnesota, Wisconsin, Illinois, Tennessee, and the New England states. I've been with Frigel for 13 years, like they said. Came to Frigel right after graduating Bradley University with my bachelor's in mechanical engineering. Started on the inside engineering team, and then slowly worked my way to inside sales, and now broke out to outside sales. A little bit about Frigel. Frigel was started in the 1960s to provide process cooling to the molding industry. Mainly that entails temperature control units, portable chillers, and cooling tower replacements for like adiabatic cooling. We started in the late 90s in the United States, and we're currently located in the Chicago suburbs, the Northwest Chicago suburbs. So for today, we're going to be talking about the critical thermal and hydraulic load analysis for proper cooling system selections. That's a mouthful. So what we're really going to be talking about is how to cool your mold properly. In this presentation, we're going to be focusing more on the mold cooling rather than machine cooling or other system cooling in a injection molding plant. So typically, most of this discussion is going to be on the mold itself. All right, keys to efficient mold cooling. To tell you the truth, mold cooling is often an overlooked process for injection molding. Typically, the molding machine and the mold, both very expensive items, get all the attention. And then for the water side, let's hook it up to cooling. Let's roll out our cheapest TCU we have, maybe one aside, set the temperature, set it and forget it, but not taking into account all the factors that we need to produce a good part. Because water, the cooling, is kind of invisible. You see the temperature, you maybe see two dials going back and forth to get pressure, but it's kind of hidden and kind of forgotten. So I want to touch on how we can make mold cooling more interesting and also provide you better performance on your tool and produce better parts. The most important factor in cooling a mold is going to be high flow and more importantly, high turbulent flow. We need a Reynolds number of over 3,000, but we need to make sure that we can actually get it. We need to look at the pumps, whether you have a dedicated temperature control unit or a chiller, or if you're flowing water directly from a central chiller system to the mold. We need to make sure that we have high turbulent flow, because the faster you get the heat out of the tool, the faster you're going to make the part. And there's going to be a lot of savings, both energy and production savings in high flow. Second, we need a sufficient pressure supply going to the tool. As we increase the pressure differential, we're going to increase the flow to the tool. And it's not just the tool itself. We have to make sure that we have sufficient supply pressures to overcome all the hose fittings, the quick connects. Maybe we have a lot of hoses. We need to make sure that we have a pump, whether a TCU or your main system, that can supply that pressure to get the water to the mold. Determination of the ideal temperature. What is your temperature set point going to be? Does it make sense for this the particular application, the typical material you're running? Highly accurate temperature control. If you have a temperature control unit, are we using a solenoid valve that's open close and it's very difficult to maintain constant temperature when you have it's all or nothing? Or do we have a modulating valve where we can kind of dose the cooling water to maintain a temperature of what, 1-2 degrees Fahrenheit? Water quality, very overlooked, but we'll go into this in much more detail in the later slides. But the water quality is really a big key on how efficiently you can cool your tool. And then energy consumption and capture. What kind of information are we getting out of the units, and how can we save energy? Optimizing process cooling, maximizing ROI by improved heat transfer. So if we can provide good heat transfer to the mold, the best ROI we're going to do is reduce cycle time, be able to make more parts on that same machine at a given time. In order to get that high or reduce cycle time, we might need a larger pump for our process, which takes more energy, but as a whole, we're going to save a lot of energy by making more parts in the same amount of time. Maintain optimum product quality by increasing the flow and pressure to the tool. we're going to get a uniform delta T and a low delta T across the mold. This will allow us to provide a better quality and repeatability, which will reduce scrap overall. Reduce mold maintenance and repair costs. This is going to touch base on the water quality, keeping your molds clean so they're in service more and not in the maintenance room. Minimize electrical costs for all process cooling components, and reduce labor, water treatment, and chemical costs. Optimize heat transfer is critical. You're going to hear me say this a lot, but minimizing the cycle time is going to be the best application for what we're talking about. To increase the flow rate to the tool, increase the pressure, we're going to reduce cycle time. It's going to be a common theme in this presentation. Control monitoring to minimize defects on startup and track process repeatability. This helps if you have a besides the press TCU with maybe more control and parameters than just a temperature set point and maybe an alarm. By controlling the control monitoring of your process, you're actually going to get information back that you can better optimize the tool for. This could be that you have an alarm value when the temperature is out of range, or the flow rate is out of range on a unit that has a flow meter or calculates the flow rate. If we have control monitoring, that will tell us that when we're going to make a bad part, it's just going to help. And then also go along with a reliable mold operation. All right, poor quality, product quality, and production efficiencies are easily attributed to improper sizing of pumps, poor maintenance, and inappropriate water treatment. You could say we are what we eat. If we provide a small pump, or keep the mold in bad condition, you're not gonna you can't really expect to get a lot out of it. Molds are very expensive. They're and they're even more expensive when you're not running them all the time, and it's causing you downtime. So what we want to look at is how can we size the cooling system, whether at the central chiller if you're going direct to the mold, or besides the press units, to best match what your mold is. Water quality. Water quality in any system is important, although it's kind of hidden and easily overlooked. This is especially true if you have an open system as a open loop cooling tower rather than a closed loop chiller or closed loop cooling tower. And if you have an open loop tower, you're constantly refreshing the water, which brings in new water, which could be hard, that plates and scales up the internal passages of the mold. This is also true not just for the mold, but also other components of your cooling system, maybe the hydraulic heat exchangers of a molding machine, air compressor, feed throats. So we want to make sure that our water quality meets the standards, that we're not going to scale up or have any biological growth that's going to clog anything. Having dirty water, plates the inside cooling passages, which reduces heat transfer, but it also can plug Y strainers on molds or temperature control units, or your main system, which is going to affect the flow and pressure you get to your tool. I thought this was an interesting diagram that I want to share with everybody. which is kind of the impact of what a layer of scale on the inside of a tool or a heat exchanger or your feed throats, actually does. It doesn't take much scale to have an insulating effect and really rob your cooling system of a good heat transfer. As you can see right here, if you have just like a millimeter layer of scale on the inside of your molds, and inside of heat exchangers, you're really taking away 50% of the heat transfer automatically. So now your chillers are going to be working harder, your pumping system is going to work harder, and your machines are going to be working harder just by that little 1 millimeter layer of scale, which if everything's working harder, well, maybe you have to maintain your equipment more, and you're also going to pay more energy. So by keeping water quality and especially scale to a minimum and keeping your tools clean, we're probably going to save money, and also it's going to affect your cycle time. If it takes 50% more with a millimeter of scale, it's going to, your cooling cycles is going to be significantly impacted. Standard mold heat transfer parameters. This is something that at Frigel we try to let everybody know. The tens is something that has been, a lot of people have been doing for many decades, maybe without even knowing it. What do you need heat transfer for the mold? Well, let's have a small 3/4 horsepower TCU, and we have a 10-degree delta across the mold with a 10 psi pressure drop and a 10-degree approach between the cooling water system and the lowest temperature you can get on the temperature control unit. And this is really what I want to talk about, because does this hold true? Perhaps at one point it did, but we really should get away from this line of thinking. And so delta T of 10 across the mold, very hard to control part quality when the inlet and outlet temperatures at 10 degrees across. Across the mold, we have a huge temperature deviation, which especially in a multi-cavity tool, the first part and the last part in the mold is seeing two completely different cooling temperatures. So your quality is going to be totally different on each cavity. 10 psi pressure differential across the mold could be right if you're just considering the mold, but if you consider all the manifolds, hoses, I go into a lot of facilities where I see a lot of undersized 1/4 inch, 3/8 inch hoses, which may not be properly sized for a tool. Maybe on a small tool, but on a big tool, you see tons of these hoses, and they just absorb the pressure. They steal it from the mold, and if we increase our pressure drop, we're decreasing the flow rate to the unit by having all these. Quick connects are also another one that just rob the tool from proper flow, and they just create a huge pressure drop and reduce the amount of flow going through it. 10-degree approach. A lot of small TCUs have 1/4 inch solenoid valves. That how much cooling approach can you get when you're sending water to the mold at maybe 20 gallons a minute, but the cooling on the outlet going back to the central system is 3/4 or I'm sorry, 1/4 inch. So if we can look at that, maybe going with a modulating valve, a larger modulating valve that can properly adjust the opening, we can get a lower approach. This is especially true on a chilled water system, and if you have molds that need to be cold. By lowering the approach, maybe we could save energy by raising the temperature of the central chilled water system a few degrees higher and save energy because we have a lower approach. If we need 60 degrees to the mold, maybe we don't need to run our central chiller at 50 or lower because of that approach temperature by a small solenoid valve. How to get faster cycle times. Interesting graph. Most of the mold cycle time is dominated by cooling. You know, opening and closing a mold. Molding machine manufacturers are getting faster and faster. You know, faster fill, faster. You know, pack and hold. But cooling time has kind of been constant, and you know, 40 to 90% of that cycle time is contributed to mold cooling. So if you want to look at the low hanging fruit to reduce your cycle time and make more product, you might want to look at the cooling time. And as you saw in the previous ones, the way we do that is higher flow and higher pressure. By getting that turbulent flow, reducing some of those tight fittings, quick connects that restrict our tool. And also make sure we have the proper TCU or proper system pressure to provide that flow. All right. All injection molds have different traits. They all have a unique fingerprint that no two are the same. And to do that, we have to stop thinking that, oh, we'll just hook up the same TCU over and over again. Maybe that's a tiny TCU to get that same cooling requirement. We actually have to match the TCU or portable chiller to the right application. So what we need to know is temperature requirement, which could be what is the approach temperature. If we have a chilled water, a mold that needs cold water, do we need a chiller, or what is our approach temperature from our central cooled water, chilled water system? If you have a portable chiller, you need to calculate the tons of cooling required. Is the chiller going to be big enough, or does your central chiller system have enough capacity to properly cool this and get down to that temperature? Circuiting channels. Circuiting channels diameter, pitch, length, manifold. These are all things to consider. The bigger is probably the better, so we could get more flow through them. As you could probably tell, I really do not like quick connects. If you have like a 1/2 inch quick connect, well, really you have a 3/8 inch connection point, because the quick connect, you know, really has that orifice that really just restricts flow. So if you're thinking, oh, I'm doing good, I have a 1/2 inch quick connect, you really have half of that. Flow rate and temperature differential. Typically, these are, you know, specified by the mold manufacturers. So we should be able to know what flow and pressure that this tool has been made for, and then we have to add more pressure differential to overcome the hose connections from either the drop or the temperature control unit. Again, understanding your molds. Maybe one temperature does not fit the whole mold itself. Maybe we need 2 temperature control units or 2 chillers to provide different temperatures to each mold half. Maybe one has a hot runner and needs a little bit higher temperature than the moving half, or different applications to provide that flow. So we want to make sure that is one temperature for the mold sufficient, or do we need multiple zones of cooling? Moving on to multi-cavity tools, I mentioned before that we need to make sure that cavity 1 and cavity 8 or cavity 64 are uniform. So when you have, you know, the part quality is going to be the same. If we have a 10-degree delta T, maybe the first cavity is seeing 50 degrees and the last cavity is seeing 60. How can we get good part performance and part quality if the temperatures are just way different? We're going to actually have two different quality parts. So for multi-cavity, we want to definitely make sure that we have a high flow rate going to them. Instead of a 10-degree delta T, we want to maybe see a 2-degree delta T, where that first and last cavity is pretty much seeing the same temperatures, or plus or minus 2 degrees. This will allow us to have better part quality. But for this configuration, it might be better to make sure that all your hoses are connected in parallel. You're not looping any, which will reduce the flow rate and increase the pressure drop. Temperature. Colder is not always better when it comes to part quality. If we have enough flow and we have enough pressure, properly sized pumps on your TCU, your chiller, your central cooling system, it might be possible to run hotter. A lot of benefits when we have turbulent flow, the proper flow rate to the tool, that warmer might make a better part. It may improve surface quality, help eliminate the nit or weld lines, but by just running that tool a little bit warmer, but having the proper cooling flow to remove the heat and not sacrifice any cycle time. So it's good to understand the temperature variability of your molds. How does your molds react to that? Can you run warmer if you have the right flow and pressure? In Chicago, it's like 90 degrees today with 60% humidity. So if you're running a cold mold, you're probably going to start sweating a lot unless you have a temperature controlled building, which unless it's medical, many people do not have. So another benefit of maybe colder is not better. Optimum temperature control is always achieved with three-way servo modulating valves. Instead of all or nothing opening and closed solenoid valves, or we can get maybe a servo valve that has 0 to 100% control and kind of can dose the system. Well, one, you get better approaches from the cooling water system, and two, you're able to achieve better temperature control deviations. So maybe instead of plus or minus 2 or 3 degrees from the set point, maybe we can get plus or minus 1, which is going to be benefit your mold and your repeatability without a doubt. If you do have direct to the mold cooling from your central chiller system, maybe it would be interesting to try a temperature control unit or a portable chiller, water-cooled chiller, to get better benefits. Central chiller systems can vary in temperature throughout a day as you bring more machines on or the temperature outside rises or dips. That central chilled water you have all the way in the back corner of your building might fluctuate 5 degrees. Which is in turn going to fluctuate your mold temperature if you have direct cooling. By having a dedicated, besides the injection molding machine, TCU or chiller, you can prevent that fluctuation and have a better standard uniform temperature going to the mold. So some things to think about if you are having mold cooling issues. Maybe it's due to low flow, too many connections. kind of put the slide here to kind of make you think that what is my process and what am I seeing issues with? And by understanding that, I know I keep on repeating this. Flow is going to be a benefit for your process. And to get flow, you need to maybe make sure that you have the correct pump. By maybe going from a 3 horsepower or a 3/4 horsepower TCU to a 2 horsepower, that might be great. It's going to be a bigger pump. It's going to provide more flow. But what is the pressure of that flow? Does it have are we topping out at 35, 40 PSI? Or are we getting 60 or 70 PSI to overcome those pressure drops of the fittings, overcome the pressure drops? Maybe you have bubblers or baffles or tight channels in your mold that maybe we need to look at, maybe not just the horsepower of the pump, but what is that pump curve? Maybe if we need a high pressure, we look at a peripheral pump instead of a standard centrifugal pump. And then if you're looking at a 10-degree delta across your mold, definitely want to look at maybe going to anywhere from 2 to 4 degrees delta T across that mold. Again, turbulent flow. Sometimes turbulent flow is hard to calculate when you're on the shop floor. You get a mold from a different supplier to run, and you have no information about the mold rather than, you know, we need this material. So sometimes getting consistent flow and knowing when you're getting consistent turbulent flow to the process could be hard. So by increasing the flow and pressure, we're definitely going to overcome some of those issues. All right, increasing stability and increasing energy efficiencies. If you are using a central chilled water system, it might be interesting to look at a portable chiller besides the press. If you have 1 or 2 machines or 1 or 2 molds that require a much lower temperature. Let's say if you have 10 machines in your plant and 2 of them or 1 of them are running at 50-degree water, the rest are running at 70 plus. Why lower the temperature of the whole central chiller system just to heat water up again for those other 8 machines when really you have to run that cold just to cover 2? Maybe a portable chiller at those 1 or 2 presses that need colder water might make sense. That way you have maybe a 2 or 3 5-ton chiller providing that colder water, while that bigger central chiller can run at a higher temperature much more efficiently and save energy. Also, by decoupling from a central chiller system, perhaps you have that one machine at the very far end of the room, last machine on the piping system, where it's just not getting a lot of flow and pressure because it's all the way at the end. The other molds, the other machines are stealing the flow and pressure from the central chiller, and the one at the end is kind of getting left out. By putting a booster pump, a chiller, or a TCU on that, we can bring that in and provide the right flow and pressure that tool needs. All right, so kind of the conclusion coming up here. A lot of it's not too difficult, you know, to kind of sum up everything here. It's just we need to get into an idea that flow and pressure are definitely our friends, and maybe that standard temperature control unit or the chiller with the 3/4 horsepower, 1 horsepower pump might not be sufficient for your mold. Now, I know the mold ranges that everybody on this presentation is going to range from a micro molding to maybe like a 1,000-ton press. So it's kind of difficult, but to kind of narrow down, but flow and pressure are definitely our friends. And we want to, if you're having issues, or you want to maximize the cycle time by reducing it, because it really is the low hanging fruit. All the injection molding machines, they're going faster and faster, opening, closing, injection, but really cooling water really hasn't changed. And taking 40 to 90% of the cycle time, it is the easiest way to increase your or decrease your cycle times. And at the same time, by getting turbulent flow, getting the heat out, maybe running a little bit more for, maybe you find it that it has better surface finish, and we're definitely going to reduce scrap. So with that, I appreciate everybody who logged in, who listened to my little presentation. I appreciate it, and I think I'll turn it back over to Weston.
Yeah, great, Dan. Wonderful presentation there this morning. We had a few questions come in while you were speaking, and we're going to have a few more here, I'm sure, start showing up. So first question I have is, how do you know if you have enough flow to properly cool the mold?
Great question. It's difficult. I mean, unless you have the cut sheet from the mold supplier, who did the testing, the sizing, the finite element analysis through the unit, or through the mold. It's hard to tell, especially if you get a mold from a different supplier that says, oh, we need this many parts. So it's kind of a guess, but to ensure, but we do have some things that we can figure out. One, the delta T across the mold. Let's make sure that we can get in the 2 to 4 degree range instead of the 10-degree range. That way we at least make sure that we have turbulent flow. We might not have the design flow of the material of the mold itself, especially on older molds. But by ensuring that we have a low delta T across the mold, we definitely can make sure that we have turbulent flow. Perhaps we are even providing more flow than the original design spec.
Wonderful. Next question pop up here is, what are some benefits of having a chiller or TCU beside the molding machine, as opposed to a central location?
Okay. So I think a big benefit is local control. If you see that you need to change temperature or you need to get information, it's kind of hard to find out by walking all the way back to the central location. But besides the press chiller or TCU, you get the information right there. You can do fine tuning, changing temperatures, but you can also add. It also acts as a booster pump right at the source. Perhaps you can lower the pressure of the main central system, because if we have a local, besides the press chiller or TCU, we're boosting the flow and pressure right at the machine, right where we need it, rather than boosting it all the way back in the corner and hopefully it finds its way to the right path, where instead of maybe like an air compressor or heat exchanger stealing it all.
Excellent. Excellent, Dan. What is a good indicator that the mold is not running as efficiently as possible?
Part quality. And hey, maybe when we ran this mold last month, we were able to get this 30-second cycle time, but now we're getting a 40-second cycle time, and that's how long it takes to make a bad or a good part. So I think the quality is definitely going to be the biggest indicator of the finished part.
Wonderful. Dan, can you explain for the audience here the difference between nominal cooling capacity and actual heat load capacity?
All right. Um, Nominal cooling capacity, I obviously is probably going to be, the specifications of the material. Actual heat capacity is, how many pounds per hour, what type of material it is, and how much tonnage of cooling it takes to remove that heat.
Excellent here. What would be some of the benefits of having a complex controller on the chiller or TCU?
Sure. A complex machine controller, probably, and I'm probably referring to something more than a digital gauge that says temperature and two pressure gauges that just go like this and it's hard to read. Having a more process-oriented controller that gives you more feedback is definitely going to be a huge help, especially for maybe process engineers setting up the mold for the first time, where you have that instant feedback to set up the machine correctly. Maybe with a higher level control on a temperature controller or a TCU, you're going to be able to set boundary ranges for temperature and flow. So if you need 70 degrees Fahrenheit, and if you want to make sure that the unit alerts you if you're going out of range, and it alerts you before you start making a bad part. Also, a lot of higher end TCUs or chillers have machine to machine cooling, so you can connect them to a molding machine via SPI, maybe a 4 to 20 milliamp or the newer OPC UA connections. So you don't even have to, you could just shove that TCU in the corner or that chiller in the corner on the other side, on the non-operator side of the molding machine, and have everything come up on your molding machine display, kind of right where it should be and right where the operator can see it.
Great stuff. Great stuff. Can one have too much pressure in their closed loop system, and would that affect how flow at the molds?
Sure. If you have PVC pipes, they should be typically rated for 150 psi. Obviously, if you have too much pressure, you might want to double clamped hoses so nothing gets blown off and you have a big mess. But typically, I think for the pressures I'm talking about are generally between 40 and 100 psi, which are definitely going to be below the rated fittings, hoses, PVC pipes, steel pipes, and connections. I would just if you want to increase the flow and pressure, I would just double check the hose clamps from the going to the mold.
Sure. Looks like, and maybe we'll see a few more questions start rolling in here. How does conformal cooling lines affect pressure and flow? And does it require higher pressure pumps for cooling?
Oh, I like that question. So conformal cooling is cooling channels following the path of the outside of the molded part in the mold. So we're getting the cooling path and the cooling channel as close to the mold surface as possible, and also following it to provide a kind of higher level of uniform cooling inside the mold. Really depends on how big these channels are. Conformal cooling, I see them more in smaller molds or portions of the mold that have like cooling issues, maybe a tight passage, or so you probably need a little bit more pressure to go through the cooling, conformal cooling. But yeah, starting to see a lot more conformal cooling. definitely a good buzzword lately. But yeah, it probably needs a little bit more pressure to go through those conformal cooling passages because they are a little bit smaller. And then the more pressure, we need to make sure that maybe a different non-conforming conformal cooling passage doesn't rob us from all the flow.
Excellent. This question we may need a little clarification on, but let's give it a shot, okay? What is latent heat of a solution, and how does it concern assessing the tonnage of a chiller when a chiller is to be connected to a reactor where the concerned solution is to be cooled?
Sounds like something right out of a textbook. Yeah, maybe a little bit more clarification on what direction they're going, Matt.
Yeah, let's give a little opportunity here for them to clarify that. With that, I'd ask for any more questions to be submitted. If you're considering anything right now, we're down to the final question here. And Dan, I want to say on behalf of Sodick and Plus Decking, thank you for presenting. That was great information.
Thank you for
Plus.
having me. It was fun.
Yeah, absolutely. I see Len just popped back on. We usually give him a second or
Great
two.
job. That was great. Thanks so much. I appreciate it. Maybe we'll look forward to Frigel number 2. But great topic, and I think it was a lot of good engagement with the attendees. That's fantastic. Thanks again so much. Good job.
We'll give him just a few more minutes here to clarify that last question if we can. I think it'd be great to answer it. Get some clarity. Dan, I see we got a lot of contact information there. Maybe you'd like to share your email address if they want to connect with you directly on any of these questions.
Sure.
Great. The previous attendee is going to reach out to you directly on that last question, Dan.
Okay.
We'll get you in touch here with him. So
Great. Bennett, Weston, thanks so much as always. And Dan, thanks. Have a great rest of the afternoon.
Thank you, everyone.
thanks,
Bye-bye.
everyone. Take care.